Good afternoon. I'm not selling anything today, but I'm going to talk to you about my experiences with scalability. I invented the DNS about 35 or so years ago, and it's still around, and it's still big, and it's probably the biggest database in the world. At least it's the most widespread. So there's some lessons from that, but I think there's lessons from a lot of other technologies. What is a scalable system? I'm going to give you my definition. It's basically something that consumes a virtually limitless resource, produces a different resource, again, in a limitless way, which means that you need demand and you need supply for all of that. And in the middle, it has to be adaptable. And the adaptability, I think, is one of the key elements. The example that everybody gives is Moore's Law. This is sort of, when you open the textbook on scalability. And basically what he wrote about a long time ago was that the feature size of a transistor was going to get smaller. So if you have a transistor that's that big red square, okay, but if you could make it smaller, then you could fit 4 by just having the feature size. And then you get 16, et cetera. And so the scalability came from making transistors smaller and smaller. I'm old enough that I remember that one of the things that I did was I tried to make some integrated circuits, and I was using an X-Acto knife on the mask. That doesn't work anymore. But that was in days when it was more like 16 transistors on a chip. But it doesn't come for free, the scalability of that. Because supposing that each of those transistors uses a given amount of power, you're also using 16 times the power. And so you have to worry about fixing a lot of problems along the way. So the reason that CPUs use lower voltages is they would melt if they were all using a traditional higher voltage. People have to worry about piling up too much charge in one place and a lot of other things. So it's not a smooth way. Even the production of the masks to actually make the chips has gone through many different revisions of the technology. So in reality, there's really several dimensions. Making the masks themselves is one dimension. Fabbing the chip is another. And then worrying about not having them melt, distributing power on the chip, clock, et cetera. There's a lot of different dimensions. You don't get it by just solving one problem. Another thing that you have to worry about in scalability is, I love the iPhone A11 chip because it had almost precisely 1,000,000 times as many transistors as the Apple II 6502. 1,000,000 times more transistors. But if you want to have the benefit of scalability there, you have to figure out what to do with those transistors. So today I want an iPhone with fast cores and a bunch of slow cores and memory and all of that kind of stuff, rather than 1,000,000 Apple IIs. So the CAD tools and the designs also have to be scalable for you to be able to, get the benefits of these resources. So CAD tools would be another dimension, I would say, of integrated circuit design that had to be conquered in order to take advantage of making the transistors smaller and smaller. A couple of other examples, I think. When you have a scalable system, one ecosystem feeds another. And what I mean by that is, we all know that physics and Intel gave us faster and faster processors. But we would have stopped if we hadn't figured out how to use up all those cycles. So Microsoft had its own scalable system where they first of all decided that you didn't need just green fixed size letters, you need variable size letters, you need to store music. You need to find more and more, less valuable in a way, uses for the cycles in order to keep the interest going about creating more. Originally all of this technology was just used for national defense, then banks and so forth, and now it's in my iPhone, having me solve puzzles. Ecosystems compete as well. So one of the questions we have, the internet protocols prevailed over the open systems OSI stack because of, well, here's a multiple choice. The genius of the fathers of the internet. That's one of the possible answers. I like that a lot because I was one of them. But the real answer here is that it shipped first in an incomplete way, but was deployable on anybody's hardware and software. So first, the real reason that the internet protocol succeeded was that there was an awful lot of power coming, just like we talked about over here with Microsoft using it for justifying text and whatever. There was a lot of communications power that was coming from both fiber optics and the use of integrated circuits to make internet over cable or whatever work. I was with one of the first companies to do that. Now, when I explain distributed systems, I start out by saying there's really three parts to all distributed systems. There's the hardware, the software, and the configuration. And you might say, why on earth do you pick those icons for those things? Well, the answer, of course, is that for hardware, you want the freshest possible. It's just like milk, all right? For software, you want something that has a little age on it, you know, like wine. It gets a little bit better with age. You know, not too many people would want to have the first software release put into their pacemaker or something. You know, it really helps to be able to mature the software a bit. And configuration is like death and taxes. It's something that you have to do in order to take advantage of the first two, and you can't escape it. And that's actually why DNS came into existence, was to try and make configuration more scalable. If you read the online DNS history, there's a few errors that creep in. I have, in different versions, had 6 different co-inventors cited on Wikipedia. So, and I didn't have any that I knew of, but at any rate. Another example is they talk about how the DNS was created by the Internet Engineering Task Force. Okay, well, the problem with that is they also say that the IETF had its first meeting 3 years after it supposedly invented the DNS. Okay, and the DNS was invented for ARPANET, but the ARPANET was shut off on January 1st of 1983. So, you know, there's a lot of fake history here. I'm going to tell you about how we got, or how I guess, got lucky in doing this design. The real history is that John Postel, who was my boss at the time, asked me to forward some kind of consensus out of 5 or so proposals that were lying around. And I mostly ignored them, but stole some ideas from them. For example, the domain name system was something I stole from a different design. Nobody thought, and one of the questions that I always get is, Paul, how did you get the job of designing this? You know, how? Was it like, you know, Survivor or something? You know, was there a competition? What was it? And I said, nobody thought it was important, so they gave it to me. I happen to think it was an interesting problem. Similarly, if you talk to Bob Kahn and Vint Cerf, the inventors of TCP/IP, in their Turing Award speech, they claimed that they could have never done it the way they did it because the importance wasn't understood at the time. So they got to have a free hand. So if you feel sometimes that people aren't believing too much in edge networking just yet, maybe that's a good thing. You know, you can innovate and create stuff before they figure out what you're up to, and then it'll be too late for them. That's the way it worked out for Vint and Bob and me. And I think it's something that we need to worry about. What were the raw materials for the DNS design? The story is over there. You know, there was this IEN. Xerox had their name. NSF wanted to, I think they were going to locate a big database in Madison, Wisconsin, instead of because the university was there and they had an NSF proposal. There was X500. In reality, this was just based upon my personal experiences. I worked on virtual machine technology at IBM. I worked at what's now the Media Lab. And at the time, the Media Lab was not important enough to get real computers. They only gave them like mini computers, and the big time-sharing machines were reserved for important things. So we had to figure out how to use a bunch of mini computers to get our work done. We didn't know we were doing distributed computing and cloud computing research, but we were. We were just trying to make stuff work. The redundancy ideas came from my work building space systems, which had to be redundant in order to be reliable. It wasn't, in those days, it wasn't so much that you could reprogram them once you launched them. And then a bunch of the ideas about computing by name were taken from Dave Farber and the Distributed Computing System project at UC Irvine. So I admit that I stole. I get kind of upset when people say that I stole from a place that I didn't really steal from, because I think, my victims, the right victims deserve the credit for a lot of the ideas that went into the project. Some of my principles that I think I'd recommend to you are, try and make something that's minimal and gets off the ground first. Don't try and do the great all-comprehensive system. The OSI people tried that. Some people say that it's no longer the case that you can have simple ideas. And I always tell them that, well, it took 40 years from the first commercial air flight, which was on a Zeppelin, to a jet airliner. That was a 40-year span. 40 years after that, somebody invented the wheelie bag. Okay? I think wheelie bags were a great idea, but there was 40 years that we were flying commercial jetliners without wheelie bags. So I think there's probably wheelie bag kind of ideas that are available to you out on the edge. You just have to kind of find them. So the initial DNS, again, had no security, a bunch of other stuff. And whenever people criticize me for that, I say it was intentional. And oh, by the way, if you look at the Wright brothers plane, there's no bathroom or a drink cart. A minimal start. So how did things scale over time? One of the ways they scale was by the applications that were attacked. People always, and you go again to Wikipedia, they say, the domain name system was created so that you could look up host names. All right. Well, that has never been the first application. The first application of the DNS was to find the right server to ask. The DNS, one of the innovations of the DNS as opposed to the other systems was you had to tell it where a root server was, but from that it could figure out where every other server in the internet was. So the first thing that it did was to be able to configure itself to find out what server to ask in a highly distributed environment. Then came host names, redundancy, routing of emails. It's the starter motor for Active Directory, stuff like that. In more recent times, 7, 8, and 9, there's actually, I think, more DNS activity having to do with stopping things from happening than in making them happen. So there's more DNS lookups for a given email message to stop spam than there is to deliver the message. Similarly, these days, when I talk to people about their DNS configuration, I say, the two things that it has to do are look up the information for you, and then the second thing is to prevent you from going to bad places. Because I think that DNS filtering, in other words, having reputation information about where you should go and where you shouldn't, is an essential part of DNS today, because there's so many bad places to go to, and there's so many ways that people can suggest them to you in PDFs, spreadsheets, email, phishing, et cetera. Avoiding going to all the ones that are known bad, I think, is an essential. And before everybody starts explaining to me about, no, that's censorship, I go, no, but I want to be in control of that. I want to be able to say, what filtering I want to have go on. But filtering itself is as essential as chlorinating water. I mean, you just have to do it, I think, to survive. Another way you can look at DNS scaling is there's all these colored blobs. And if you take a look at the two little ones over on the, I guess it's the left-hand side, those are the two RFCs that I wrote. Each blob here is an RFC, which is a potential internet standard. It's a separate document. So this is really great, because starting out with my two over there, all of these other things that I had nothing to do were built on top of the DNS to add features and so forth and so on. So I always tell people that the DNS is like an 80-story building, and I built the basements and the first floor. And all this other stuff was invented by other people. And so that in one hand is very successful. I'm sorry, it's too small. You can't read the titles inside the blobs. But what about failures? What did we learn that we shouldn't have done? Well, one of the things is that chart from before, means that if you decide, by gum, I'm going to go work on DNS, you have to sort of start by reading about 100 RFCs, 100 of those documents, if you want sort of a comprehensive understanding. Why is that? Well, nobody is really interested in putting together all of the existing documents into one comprehensible story. So a bunch of those documents partially update the previous ones. There's no one coherent documentation of the DNS pretty much anywhere. There's a couple of people that have written books, but the standard now is so diffuse. That's a problem. And people, it turns out, get awards from their companies for writing an RFC, but nobody has been able to really do the task of trying to get back to one or two unified documents. The original specs that I wrote had one part that was sort of the theory, and the other was implementation details. And I anticipated that the implementation details would change, but I tried to get the theory so that it worked forever. But we don't have that anymore. And the standards organizations that define the DNS, are they the IETF? Well, yeah, but there's also Microsoft, which has its own variant, and Cloudflare, and all of these guys. They all have their own versions of it, which is another thing. So when you're trying to put your standards together for all of this Open 19 thing, you got to try and remember that the more readable your standards are and the more sort of coherent they are, the more people you can get working to give you a boost. Another scaling failure is the data links that we use today are about 1 million times faster than what we had way back when. But the packet size is about the same. Some of you may remember ATM cells that were supposed to be small. Well, maximum size Ethernet frames in terms of time these days are much smaller than an ATM cell ever was. Why is that a problem? Well, for example, if you try and use datagrams in DNS and you want to have a digital signature, the digital signature chews up most of the 500 bytes that you get a payload, 512. So we haven't scaled that, and there's a lot of middleware boxes out on the internet. This is a broader failure that won't let you pass large packets. So datagrams are sort of dying off for a bunch of reasons, including DDoS. But we really need to think about, well, why can't we get a little bit more efficiency out of that? Because I think it would simplify a lot of things. And of course, there was commercialization. The DNS, I think, today should probably be written as a $, as the S. A friend of mine who created the Interrupt conference says that I'm the only guy he knows that created a $1 billion industry but didn't get paid for it at all. It's sort of true, but there's a lot of financial incentive to do strange things to the DNS, and that's why we're starting to see centralization, where I think it's time to see more distributed approaches, particularly if you want to have a reasonable amount of security. I'll be happy to talk to people offline if they want to debate that with me. The security problem in general is really a scalability battle between you and the attackers. It's really a question of economics, and it's really a question about how scalable your defenses can be against the attacks as they scale up. There's this complicated relationship, but basically you want this inequality to hold where the cost of the defense is less than the cost of an attack, and also the value of the target is in the middle. We have to start thinking, I think, from the start about building security into systems, but more is the point, the security has to think about being cost effective. Having complicated software solutions in CPUs, I don't think is the answer, because unfortunately the fiber optic guys and the hardware guys can bombard you with more stuff that you can evaluate in software. So how are you going to deal with it? I think that's one of the open questions. I've been curious about 5G for a long time, and IoT and edge, et cetera. So I'm going to tell you about what happened when I asked an expert. And when I say expert, this is somebody that organizes a 5G conference. I said, what's the best paper to read about 5G to kind of understand it? And they sent me to this. He's in Europe, so I can understand why. And so the Boston Consulting Group, they're consultants, they must be very smart. They basically said, well, 5G is the only way that we can cope with the growth of mobile handset devices in sort of like a 4G kind of way, in a cost-effective. So 5G is a cost-effective replacement for 4G scaling. Okay. Well, what are the other interesting use cases? Well, the ones they talked about were autos, but they claim that somehow or another the auto dealers in some conspiracy have gotten too good a deal. I know that I bought a new car, and it has its own cell phone number, and I guess you can't buy a car that doesn't have a cell phone number these days. So I'm curious to know what the great deal was. Maybe somebody out there can tell me. I really don't want cars that have to rely on having a 5G connection in order to stay safe. I mean, I just think that this whole idea about having systems that are flying or driving that rely upon a telephone connection or a 5G connection, I think they have to be a little bit autonomous. Maybe they don't know the right way to get you to the closest McDonald's, but they should be able to not hit anything without having that. Fixed wireless is the thing that people really talk about. Now, if there's somebody out here that wants to educate me further, that'd be great. When I think about it in the context of edge systems, I sort of say, well, going back to my chart of what is a distributed system, it's clear they have the milk, but I'm not really sure they have the wine or the death and taxes yet down pat. It seems to me that there are some needs out there that I don't quite understand how they're being addressed. Since I do DNS, well, what might the needs be out at the edge? I think there's DDoS defense. DDoS is a much larger problem than most people think of. The traditional DNS has 2-second timeouts if it loses a packet. Well, okay, but if you want near zero latency and you want to go faster, we need to think about speeding it up. Again, I think that there's the filters and firewalls need to be out there at the edge if you want to have performance. IoT devices in particular can't protect themselves. We work with a couple of hospitals, and they want to have a lot of filtering on both the IP and the DNS level because they have devices where they're legally required not to change them, i.e. they can't install updates because they don't own the device. And if they install the update, they'd be modifying it and breaking two different kinds of laws about safety and the ownership. So they need to be able to be segregated. The whole business about not having lines of defense anymore, I think means no, we have more of them and they're around every device. So we need to figure out sort of basically how to mass produce private intranets so that these devices can cooperate in restricted ways within the context of a hospital or whatever. I mean, I was very surprised to find out in a traditional automobile that the radio can usually send commands to the brakes. The CarNet, I think it's called, it doesn't even have a source address in a packet, so anything can send. So you could theoretically put in a CD that has a virus into your CD player, infect the CD player, and have it turn on or off your brakes. Like, no, you can't do that. It's not safe. And of course, the whole idea about having a 4G connection to the outside world just makes this all much worse. Whoops. I'd like to be able to think about free association, though. I mean, we have a bunch of stovepipes that are out there. Doorbells talk only to the cloud services that sold you the doorbell. My Chromecast device will only use Google's DNS. There's all of these stovepipes. And I want to be able to basically tell all the devices that I have which other devices they can talk to and forget it. There's some work in the IETF to do that. But if you don't know what can talk to what, I don't see how you ever secure it. We think we need more in the way of per user databases. We tried to do that for mailbox names. We didn't succeed. But I mean, one of the problems you have with cryptocurrencies these days is that there's no real way to identify your counterparty. Or perhaps there's about 200 different ways to identify your counterparty and no one standard. And again, the mass-produced kind of private systems. So I'm about done. I spent several years at the University of Marie and Pierre Curie, and I found out a couple of things. So I'm just going to try and pass it on. She won 2 Nobel Prizes. Pretty cool. And she probably died as a result of her work. She used to run around during World War I with a bunch of radiant sources in her pockets so she could bring them out to field hospitals that wanted to do x-rays. If you're ever in Paris, you can go by and see her cookbook. Of course, you have to sign a waiver and wear lead gloves because it won't be safe to touch for about another 200 years. And all of this is to say that, discovering things, you ought to be a little bit careful, I think, in particular with blockchain and some of the DNS settings. We have to be careful in the way that we deploy and use this technology, because I think massive security failures and other kinds of bad consequences could be much worse than we think of today. So that's what I have to say. I'm not sure that we have Q&A now or the next speaker, but I'll let the administrator let me know.